let's go back to this issue. So we have three candidates and there is voting. X1, X2, Xn is the voting between A and B. +1 is for the first candidate. So for B versus C, it is Y1 through Yn. For C versus A, it is Z1 through Zn. And the assumption is that for any I, if you look at this column, X1, Y1, Z1 is not 1, 1, 1, which means just same as saying that the first voter has a clear preference between the three candidates. If it's 1, 1, 1, then the first voter prefers A to B, B to C, C to A. That doesn't make sense. So we assume that this holds, that Xi, Yi, Zi. So then what we did was to make this random. Okay, so we made the assumption, so in calculating the probability, we took Xi, Yi, Zi independent and uniform among all possible tuples, except it's not allowed to be 1, 1, 1 or -1, -1, -1. And then we calculated the probability that there is no Condorcet winner. Condorcet winner, you may recall, is that, so from this voting, we apply a Boolean function to get decision f of x. Similarly, f of y, f of z. F of x is 1 means A wins over B. F of x, y is -1 means C wins over B, etc. So the question is whether this leads to an unambiguous ordering of the candidates or not. So the problem is if fx equal to fy equal to 1. If fx equal to fy equal to fz. If it's 1 or -1, then there will be ambiguity. So the probability that there is no Condorcet winner is this probability, which using Fourier analysis, we brought it to this form. Up to this is a up to this point here, this is equality. So that probability is precisely this, the probability that there is no Condorcet winner in Fourier expression. This is 1/4 plus 3/4 2 to the n times sum over all subsets f hat of s squared times -1/3 to the power of cardinality s. Okay, so this is what, and then from there we showed that if this has to be 0, that the only choice is first of all the f hat of s should be 0 if cardinality s is not 1, and hence we get something. And then we argued that f has to be actually a dictator function. Okay, so that was the gist of it. And what we are proceeding towards is the robust version of this, or stability version, which says that suppose f is from z2 to the n to -1, 1, some Boolean function which we used to decide between votes between two candidates. And in a three-way election, suppose the probability that there does not exist a Condorcet winner is less than equal to delta. Okay, so we are assuming that in this situation, it's not that there is always a Condorcet winner, but we give up. If it's a very tiny probability that there is no Condorcet winner, we can probably still go ahead, conduct the elections and hope to get a result. So suppose the probability to not get a Condorcet winner is less than equal to delta. Then fx is actually equal to the dictator function on a large set, or equal to the anti-dictator function on a large set. So here it's not 0, so you can't say f will be the dictator function, but it will be fx will be equal to xk on E complement, or fx equal to -xk on E complement, where E is a set of small probability. Proportion to 2 to the n is small. Okay, that's the theorem we are getting towards. Okay, so now there will be a few ingredients needed. So let me start on them. First, let me take this expression and rewrite a little bit. Okay, so as part of the preparation, so this one is a relatively simpler one. The reason I am actually going through this theorem, I would have just stated this theorem and said that, okay, it is there so that you know. But I'm going to the proof of this because we introduce a rather deep concept in this whole business, actually. Maybe the deepest thing we have seen so far. I'll come to that. But this one is a simpler point I'm going to make. Preparation for the proof. We have already seen that probability no Condorcet winner that probability we wrote as 1/4 plus 3 over 4 into 2 to the n, sum over all subsets, minus 1/3 to the power of cardinality s. Okay. And what we did earlier is just bounded this from below. Earlier we just used the bound minus 1/3 to the cardinality of s is greater than equal to minus 1/3, because for even cardinality it's positive. For odd cardinalities, the best is when s is 1. Cardinality s is 1. Then it is minus 1/3. Otherwise, it's a kind of smaller negative numbers, meaning smaller in absolute value. But now let's do it a bit more clearly, because we want a quantitative one. What we will do is we'll keep the s equal to 1 case separately and get write better bounds for the later ones. Okay, so that's what we will do. So first of all, we can drop all the. So if you want, you can drop all the even coordinate. Okay. Cardinality s odd, and then f hat of s square, or actually, so maybe, yeah, it's not necessary to write this. So let me just. So let's write the case when s is 1. Cardinality s equal to 1, we'll get a minus 1/3, right? F hat of k square. Okay, I should write f hat of the set singleton k. But okay, I have written it, I will not change it. Minus 1/3 will make this minus 1, right? So this is what we get from the s equal cardinality s equal to 1 term. And in the remaining parts, what we will do is we will bound it by in the remaining parts, the positive ones can be anyway dropped. Okay, so this is a greater than equal to. Positive ones don't have to worry. It's the odd ones that we need to worry about. So once we have kept the cardinality s equal to 1, in fact, we can bound this by minus 1 cube if cardinality s is not equal to 1, then the next best thing is minus 1/27, right? So we can use that. So what we will do is we'll bring the minus 1/27 here. So that will cancel 3 and I'll get 4 into 9. Cardinality s not equal to 1. F hat s square. Is this okay? So all I'm saying is that earlier we just bounded this minus 1/3 to the s by minus 1/3. Now that is when cardinality s is 1. Now we have pulled that out separately. In the remaining, we can bound it by minus 1/3 cube, because that's the next odd number. Okay, so that's what we get. Now this is actually 1/4 minus 1/4 into 2 to the n summation f hat of k square, and because L2 norm squared is norm f2 square is 2 to the n, right? Because f is a Boolean function. So if you sum of f of x square over all points will give you 2 to the n. Therefore, what I'll get here is this one, and this is also equal to summation f hat of s square over all s by Plancherel's theorem. Okay. So therefore, if I sum over only s with cardinality not equal to 1, after dividing by 2 to the n, I can write it as 1 minus. Sorry, 1 second. So f hat of k square. Okay. Minus 1/36 into 1 minus this. So do you understand this? I'm just using Plancherel's theorem. 1 by 2 to the n times this is actually 1 minus this. Sorry. Okay. Sorry. That's not correct. 1 minus 1 by 2 to the n of this. Is this okay? I'm just using Plancherel's theorem, and the fact that f is a Boolean function means its L2 norm squared is 2 to the n. So which is summation f hat of s square. And so this sum is sum of f hat of s squared. That will be 1 minus this thing. Okay. So so if there's a question, you can ask me. So anyway, this is actually same as this is what we have here is also the same. So this is 1 by 4 into 1 minus 1 by 2 to the n this. So the overall we get 1 by 4 minus 1 by 36 into 1 minus okay. So 1 by 4 into 1 minus 1 by 2 to the n. That same thing I have here. So you get this, which is how much is this? 30.
Manju, you are missing the 1 by 2 power n.
Oh, sorry. Again, 1 by 2. 1 by 2 to the n. So this is 32 by 36, which is what is 32 by 36? Yeah, 8 by 9, is it? Is this correct, or have I made a mistake? Is it 1 by 36 or is it something else here? Okay, maybe it is correct.
It's 8 by 36, no?
Or is it? Okay, sorry. 32 by 36. So I did 8 by 9, right? Oh, sorry. What is it? It's 36. Okay, sorry. Yeah, so, sorry. This is 9 by 36, right? So it is, yeah, so isn't it 8? Oh, it's 8 by 36, right? Okay, sorry. 8 by 36 is 2 by 9, is it? 4 2s are 4 9s. Yeah, 2 by 9. This is correct. Okay, so we get 2 by 9 into 1 minus this. So what this means is, so as a consequence, the way we will use it is conclusion. See, we are going to make the whole thing quantitative. We have to make this proof quantitative, but it's not a very simple, I mean, it's not entirely straightforward. Some points are straightforward. This is a straightforward point. Earlier in the proof, what happened was, if there is always a probability that there is no Condorcet winner is 1, I mean, is 0, then basically we had to have f hat of s is 0 for s cardinality s not equal to 1. Now we only have that if probability of no Condorcet winner is delta, at most delta. What we have to conclude, I'll write here. So if probability of no Condorcet winner is less than equal to delta, then this whole quantity is this probability, right? At most this probability. This is delta is greater than equal to this. So if you write down, so you'll get 9 delta by 2 greater than equal to 1 minus summation f hat of k square. So we get the conclusion in this form that the singleton sets carry most of the, there's a 1 by 2 to the n again here. So 1 by 2 to the n summation f hat of k square, the singleton sets carry most of the weight. 1 minus 9 by 2 delta, which I'll just write 1 minus 5 delta. Okay, it's at least 1 minus 5 delta. So this is the quantitative way of converting. We have to again get back this point that f is somehow largely made up of singleton characters. Okay, chi s with cardinality s equal to 1. And then we will, but it's not exactly correct. So it is close in the sense that the Fourier coefficients most of the Fourier coefficient weight is on these singleton sets. They carry 1 minus phi delta of the weight. The remaining carry the remaining phi delta of the weight. Or equivalently, if I take G to be this f hat of k chi k equals 1 up to n divided by 2 to the n by 2. So this means I am taking the Fourier expansion of f, but only taking those terms which correspond to singleton sets, right? Then norm f minus g L2 norm squared is bounded by phi delta times 2 to the n. Okay, because f minus g norm squared by 2 to the n is exactly the remaining part of this. I mean the f hat of s squared over all s not singleton, and that will be at most phi delta. So this will be the first step in the proof. We will approximate f by this linear polynomial g. F and g are close is what we have shown. Now g is now we have to argue that g is actually supported. This is actually one of them takes over most of it. So G is close to a dictator. So the remaining part is showing that G is close to a dictator. F is close to G is okay. G is close to a dictator is what we need to do. Any questions about this part? This is the easy part. Any questions, comments? Okay, so there should be one question which nobody asked. Okay, or maybe it was clear to everyone, but I should point out, I forgot to say it last time. See, what is this sense in which f is close to dictator? Okay, so this theorem is saying that f is close to a dictator function, but in what sense? It appears to be in an extremely strong sense that on an exceptional set, I mean, outside of an exceptional set of small proportion, f is actually equal to the dictator function or the anti-dictator function. So there could be, but actually it's not as strong as it looks. I mean, at priori it looks like a very, very strong conclusion, but it is because these are Boolean functions. So a point to note is the following, that this statement is not as strong as it sounds, or well, other things you might think are weaker are actually as strong. So what I mean is this. So if f and g are Boolean functions, then for any x, fx minus gx is either 0 or 2, right? Because they are plus minus 1, either they are equal, in which case the difference is 0, or if they are unequal, the difference is 2. What this means is that if you look at L2 norm squared, I just write 2, right? L2 norm square, that will give me 4 times the number of x such that fx is not equal to g of x. So the set, so L2 norm square gives you is basically up to a factor of 4, same as the cardinality of the set where f and g differ. So this theorem is stated in form of this, that f and g are equal on a set of large cardinality, but equally you could write, so this statement is actually equivalent to f minus chi k, or plus or minus one of them, 2 norm squared is less than equal to 10 delta or something like that. Okay, 10 delta, this you should divide by 2 to the n. Divide by 2 to the n, then. So it's not like, so it is actually a statement about L2 norms. You could equally well say that. Because these are Boolean functions. If you are considering general functions, general real valued functions, then this kind of statement is way stronger than saying in L2 norm square. Okay, I mean, in the sense that you would be saying that, oh, it's for some reason actually equal to this. the difference is actually 0 on a small, but that's not the case here, because for Boolean functions, either they are equal or their difference is bounded below, namely 2. That's the reason why this is equivalent to an L2 norm square. Is this okay? So this is just to give a sense of the closeness in which we are proving this theorem. For that reason, this f minus g L2 norm squared is actually the right kind of closeness. This is good enough for us. So the step 1 we have done is that if probability no Condorcet winner is less than delta, then f is close to the linearization in L2 norm. Okay, so that's the first thing. Okay, any questions so far? So there's more steps, but that requires one important concept. As I said, I will introduce a rather deep thing. So the reason why I'm giving the proof is because it uses this deep fact. So I will go and state that. Okay, so this is called hypercontractivity. So forget for the moment this theorem and its proof and all that. We are moving away. We'll introduce this concept of hypercontractivity and later come back to the proof of this theorem. Okay. So I will go to this thing called hypercontractivity. What is hypercontractivity? I want to explain that. Okay. So remember, the operator we defined semigroup Qt f of x equal to so let me introduce this notation right away. F hat of s is of x. So where with rho equal to e to the minus t. So this was the semigroup that we were talking about. Always I will write just for simplicity I will write rho equal to e to the minus t. Okay. So this is something that we introduced when Q0. So remember that Q0 is identity. Q0 is identity, whereas Q infinity f. When you put t equal to infinity, all this rho becomes 0. What you get is f hat of empty set over 2 to the n by 2 times the constant function 1. Okay, so that is the this Qt is an interpolation between f and its average value. That's what it is. It's like the average value, yeah. So this is something that will come. So one of the exercises, you may remember that I had strongly recommended you to, we had given an exercise given earlier. So we saw many properties of Q sub t. One thing I left as exercise, that Qt as an operator from LP to LP has norm 1. For all p in 1 to infinity included. So one way is clear. So Qt of 1. So the point was Qt applied to the constant function 1 is in fact the constant function 1. Okay, for all t. This is true because if you put the constant function 1, then all the other Fourier coefficients are 0. So this is not doing any change actually. So that is true. So which implies that the Qt P to P norm is at least 1. So the key point here is the other way inequality. So that it is less than equal to is the non-trivial point. Okay. So this is saying that Qt is a contraction from LP to LP for every P. Now comes this very deep fact of hypercontractivity. Okay. So let me state the theorem and then explain or try to explain what it actually is saying. Hypercontractivity theorem. That's right. So this is actually, this has a long history. You can look at in the book of Van O'Donnell. He has worked out the history nicely. So first it was done by a harmonic analyst, Aline Bonamy. So she actually proved many of, so I don't know in this full form or not, But then there are many others who did in probability related contexts, Nelson and Gauss. So probability, some quantum field theory, something like that is there. Some history is there, but we don't need that. As stated, as we stated, I mean, so this Nelson and Gauss actually didn't do this. I mean, what they did was some analogous thing for Gaussian. Okay, in some sense, what they did was for the actual heat equation. You remember that I said that this Qt is like heat equation. It was very similar. D by dt Qt of f of x was minus LQT, right? So there was the heat semigroup. So this d by dt, so it was very analogous to the heat equation, right? So, but there is actually a semigroup associated to the actual heat equation, namely the Laplacian in continuous space and so on. So what Nelson and Gauss did was to take Bonomi's theorem and extend it to that setting, so Gaussian. But anyway, we will not go there now. For us, this is the hypercontractivity theorem. Okay. So what does it say? So if so let okay, so fix any p and q, p smaller than q. So what we will ask is here qt was contraction from p to p. Can it be a contraction to a higher LP space? Okay, it's going so then we say that qt from p to q is also a contraction. It's a contraction. Okay, so less than equal to is the main point. Okay, so equal to means the less than equal to is the main point. Maybe I'll even write it like that. It's actually equal to, because you understand that one constant function anyway is there. So let's just write less than equal to for all whenever, but it's not always true, whenever this t is sufficiently large or rho is sufficiently small. Okay, so when rho is sufficiently small, then this is actually that means t has to be sufficiently large, right? Then it is true that this is a contraction. So this is I mean, it's actually I personally, when I saw this statement, it didn't mean anything to me. What is it saying? What is it good for? It's not clear actually. Even now, I don't understand it too well. I will explain what I understand, but it is, we will see its use. So it is, of course, a stronger conclusion. That part is okay. That it instead of so let's discuss a bit. But before that, are there any questions about the statement? Is it clear what it is saying? So rho is always going to be for me e to the minus t. Okay. So this is the hypercontractivity theorem, and without doubt, this is the deepest fact I have so far done in this course. Okay, so it's something non-trivial. So let's discuss a bit. What is this saying actually? So first of all, for any g, if you look at the LP norms, okay, so what is LP norm? You remember that I don't normalize, right? That's why let me just write it in fact. So this is the LP norm of G. How does it behave with P? Okay, if I change P from, as P goes from 1 to infinity, what will happen to this LP norm? Yes, anyone?
Will pick up the maximum value. Yeah.
Ultimately, but as P increases, this is an increasing function. You're right, as P goes to infinity, the maximum will get picked out. But in fact, this is increasing in P. Okay, so why is that? Well, it's kind of the same reason. You see, what happens when you have a bunch of numbers? So these are positive numbers, right? Let's say you have 3 positive numbers. When you raise them to a power, higher power, then the larger numbers get more weight, right? I mean, in proportion. I mean, you're raising them to a power. Okay, so the larger numbers get more weightage, so to speak. So I will leave you to figure this out if it's not entirely clear. Okay, so because of this, but this is an easy point. But because of this, so but don't get confused. It's not. I mean, how you define LP norm is matters. But anyway, this is correct. So now, because of that, what we are saying here is that hence what we are saying here is that it is a so the conclusion of hypercontractivity, which is QTF LQ norm less than equal to F LP norm. Okay, LQ norm of QTF less than equal to LP norm is stronger than the conclusion that QTF LQ norm less than equal to norm F LQ norm, which is what you had earlier. When you said this, you meant QTF LQ norm is smaller than equal to LQ norm of F. So that is so this is stronger than this. But of course, this is valid. Of course, this is valid for all T. This is valid for large enough T. Okay, valid for large enough T. So at least it is a stronger statement is kind of clear. Okay. So but what is it actually saying? So let me just 1 second. Let me consult my notes. I had made some points to mention about this. Okay. So here is another point. So why it is for large T? Okay. So consider extreme cases. Okay. First consider extreme. So why? For large T. Okay. Why do we need this large T business in this here? So consider the extreme cases. Okay. So fix P. Fix P and Q, P smaller than Q. I mean, equal case is trivial. So fix P less than Q and consider the extreme cases. What are the extreme cases? First case is T equal to 0. Now, Q0F is F, right? So for what P and Q will it work? Holds only if Q equal to P, right? Because if Q, I mean, so this is FQ. We already said it is increasing, right? It is increasing in P. So LQ norm of F won't be smaller than in general. Okay, holds, let's say in general. If you take constant function, its LP norm will not change with P. It is the same in all P. Or no. The way I have written it, it is changing, right? No. What will it be? It will be 1, 2 to the n. No. Sorry. Yeah. So, sorry, not constant function. No, constant function LP norm is actually 2 to the n over P. No, something is strange there. Hold on.
It will be decreasing.
Ah?
It
be decreasing, I guess, if you look at the constant function. Maybe that statement isn't.
Oh, this one, did I make a wrong statement? Hold on, sorry. Is it, yeah, if you take the constant function, you get 2 to the n to the 1 by p, which is actually decreasing in p. So what did I say then? Maybe it is true when I divide with 2 to the n, is it? It's true in case of probability measures, right? Not with, yeah, sorry. That's the mistake I made. So then, okay, hold on. So then I have made a mistake here. Yeah, what did I do? Right. Okay. Okay. So this is actually a wrong statement. Sorry, this is true in when you take a probability measure, right? So this is not true when. So this is not correct actually. So as the constant function shows, I made a incorrect statement. Did I? Okay. Now I got confused myself. So if this is not increasing. What is increasing is actually, if we take 2 to the n by p, that will make it 1 by 2 to the n. This is increasing in p, right? With respect to, am I right about this? If you have, so then at least constant function has constant norm under this rescaled norm. But that makes a big difference actually. So that has to be, the scaling depends on p. So what I said here is actually not. Yeah, okay. So maybe the point is, okay. So yeah, so the spirit of what I said is probably correct, but what I said is not strictly speaking correct. For the moment, let me erase this. So if you take this, so this is not exactly speaking stronger in the sense, but the point is that boundedness is stronger. Okay, so okay, for the moment, let me, yeah, how should I fix it? So the constant here, it is telling that this is bounded by, actually my statement itself then may require a restatement. Okay. Oh, I made a mess. Now I realize that whether, no, I made a mistake here. So in whether, sorry, here I think the norm is not 1, it is actually different. Okay, so I should use this, if I use the 1 by 2 to the n norm, then this is 1, I believe. Otherwise, see, the problem is the following. Okay, so what mistake I made is when you consider p to p, when you consider p to p, what you are saying is that QTF P norm less than equal to P norm of F. Now, whether you consider the norm as I defined it or the rescaled norm, it doesn't matter because both sides will get rescaled, right? Which norm you consider, whether the original norm that I took, which is without the 1 by 2 to the n, or the one with 1 by 2 to the n will not matter here. However, so we can, so do with norm P or with but when I look at different P and Q. Now this constant is not going to stay the same. This constant is different for the two norms. So because this side you will scale by 2 to the n by q, and that side you will scale by 2 to the n by p. In fact, what I think is, okay, I even this statement itself, yeah, actually, yeah. So this is actually true when you use the, Yeah, so this is true when you use the probability norm. So if I did not use that, I will get a ratio here, which is of the form 2 to the n by p and 2 to the n by q. I will get that ratio will come here. So, this, but okay, so is this okay? I mean, will it be too confusing if just for this theorem I shift to the p norm? Because now I realize I made a mistake actually in writing down things. Is this okay?
Yeah, Manju. I think that should be okay because.
Yeah, so it's actually I mistakenly thought it's anyway scaling invariant, so I don't need to. I was generally being careful when copying results from the book because this Fourier transform normalization, norm normalizations are different. But here I thought that both sides scale the same way, which I realize now is not the case. Okay, so this is for this norm. Okay. Maybe, yeah, I don't know whether I should use a different symbol now or what I should do for this because it's slightly contradicting. Let me just to keep ourselves straight, let me put a triple here. Okay.
Yeah, I think that would be better.
Yeah, so then I'll not run into confusions later. So. So here,
so is there a reason why you didn't define the earlier norm in this fashion?
well, it's a choice one has to make at some point. It will not go away entirely. Somewhere or the other, it will show up actually. So I thought in general groups, I'll keep the counting measure that made the, what was it, the Plancherel theorem didn't have any factors. It came out as, I think, if I use this one. So because, you see, when I group and G and G hat, both are finite sets. So if you use the probability measure on this side, you would have to introduce weights on the other side also.
Right.
Something like that. So that is the reason I made that choice actually at that time. But here it is important that we keep this straight. Okay. So then this is all okay. So then the first statement I said is okay, provide with this triple norm. Okay, so this triple norm is this one is increasing in P, and hence this conclusion is stronger than this one, but this is equivalent to when you have the same Q on both sides, we can rescale, and then that will give us this. Okay, so that is the point. Okay, now I come back. Sorry for the confusion. Is there anything that I need to explain further, or is it okay? Now we are using this triple norm, which is with respect to the 1 by 2 to the n business. Okay, is that all right? So now coming back, I will explain what is the why this large T anyway. Why this large? You can state it in terms of the usual P norm, except that instead of 1, you will have 2 to the n by q by 2 to the n by p, or vice versa, something like that. Okay, why for large T? Why do we state it for large T? The point is, if you consider the extreme cases, so look at Q naught F. Q naught F is identity. Now this again, I have to now write triple norms. This, since it is increasing in P, it is holds only if Q equal to P in general. It can increase from P to Q. So this holds only when Q equal to P. Now, where suppose T is infinity. What is Q infinity F? It is f hat of empty set over 2 to the n by 2 times the constant function. So if I look at the triple norm Q infinity F, any LQ norm, okay, that is actually it's a constant function, so its LQ norm is the same always. Okay, in this triple norm, its LQ norm is constant, is actually same as f hat of phi divided by 2 to the n by 2. That is the norm in any Q. For all Q, this is yeah, because the constant function has norm 1. The one constant function 1 has norm 1. Now this is what can we say about this one? F hat of phi is actually fx divided by 2 to the n by 2, right? It is f in a product with the trivial character divided by 2 to the n by 2. So this is actually 1 by 2 to the n by 2, or since there is absolute value, I can write this is less than equal to mod fx, which is actually the triple L1 norm of f. So
I think should be 2 power n, no? Yeah, there is two of the.
Two, yeah. So this when this, yes, right. That is why I get yeah. That's important that it is 1 by 2 to the n, which is why this is equal to the triple L1 norm of f. Thanks. So this is true for all Q even infinity. Okay. So this means this holds for, so that means that is Q infinity f LQ norm less than equal to Q infinity bounded by f LP norm so less than equal to LP norm holds for all P greater than equal to 1 and Q less than equal to infinity. Okay, there is no problem at all. This always holds. Even with P equal to 1 and Q equal to infinity, it holds. Then if you increase P, this will only increase, and if you decrease Q, this will only decrease. So point is, at time 0, it holds only when Q equal to P. At time equal to infinity, it holds for all P and Q. So what hypercontractivity is doing is for finite, for any P and Q, there is some time. Okay, or for any, you can put it either way. So for any finite, what hypercontractivity is doing is gives intermediate conclusions. So one way to say it is for any P, if you take for any P in 1 infinity and any time, there exists a Q which is strictly bigger than P such that QTF, I just can write QT, P to Q is less than equal. For any time, there is a slightly larger Q for which it holds, or for any P less than Q, there exists T such that okay, so you can, it's an intermediate conclusion compared to the two extremes. Is that okay? I hope that maybe sheds a bit more light on what this is doing, giving stronger conclusions. There's another nice interpretation of this related to Holder inequality. So let me just consult my notes again. Yeah. So now let me go to the semigroup. Another way to interpret this. Okay. So you remember that QTF. What was QTF inner product G? So there was a meaning to this. So if you remember this QTF inner product in terms of the Markov chain, I will just quickly recall, is the expected value of fx into G fx0 gxt. Where xt is the mark. Introduced. I will go back to that page and recap. So just what was the Markov chain? So in doing the heat semigroup, I also gave a Markov chain interpretation of this. So we can start with this Markov chain where you start with a state. States are points in Z2 to the n. So you start with some x. Then above each coordinate 1 to n, there is a Poisson process. There is a line and there are these clocks which ring. Okay, so there is a clock which rings after every exponential random variable. Meaning there is a sequence of IID exponential random variables with mean 1, and this clock rings at those times. And similarly, 2 has its own clock, it rings at its own times, and so on. Each of the n fellows have their clocks. What happens is when the clock rings above 2, that voter changes his mind. Okay, so was voting for +1 will switch to -1 or vice versa, something like that, or maybe refreshes. They are very equivalent, so let me not worry about that difference. So, and QTF of x was just expected value of f of xt. Okay, so QTF for x, I mentioned to you that this is this. So if you take QTF inner product G, so here if you take QTF inner product G, what do you get? You get QTF of x G of x over x in Z2 to the n, which is G of x expected value of x f of xt, right, over x in Z2 to the n. So if I add an extra 1/2 to the n factor here, let's do that. So then this can be thought of as expected value of G of x into f of xt, x0 into f of xt, where x0 is picked uniformly at random from Z2 to the n. Okay, so if you accept this QTF at x is the expected value of fxt if you start from x. Now you average over x. Okay, when you take inner product of QTF with G and normalize by 2 to the n, it's the average of QTF of x, G of x, which is like this. Which is, in other words, you pick x from Z2 to the n with probability 1/2 to the n each and start the Markov chain there. So that's what this is saying. Okay, expected value of G of x0, f of xt, where x0 is uniform. You start at a random point and let it evolve and see how G at time 0 is correlated with f at time t. That's what I am saying here. Okay, so that's the, so this is what I have written here. Any questions about this? Is it okay? So, but what is x0 and xt? So x0 and xt, which we can write in a simpler way for fixed t, then this we can write as, just for simplicity, let's write like this, fx gy, where xi, yi are independent, expectations are 0, and the correlation is exactly that rho. So you may remember that the correlation between xt and x0 from this Markov chain will be e to the minus t. At the beginning, they are perfectly correlated, and as time progresses, the correlation decays. So what is happening is this. Xi, we can write it in this way. This is similar to another thing I wrote last time about stability and so on. So x and y have correlation rho. Otherwise, they are uniformly random.
That is fxt, right? Gx times fxt. The first equation.
Okay. Gx, actually, it is the same. Because of this, you see, it is actually the same. But you're right. Let me keep it straight. Because the relationship is actually, that's a reversible Markov chain. So, but just to be consistent with what I said earlier, let's keep it as g of x not f of xt. So then we can write it like this. So now, so just take this, okay? QTF inner product G is this. So what is it that we can say about this? So expectation, so time t equal to 0. Again, let's interpret time t equal to 0 and time t equal to infinity. Okay, I will end with this. Time t equal to 0, we have expectation fx into gx itself. When time t equal to 0, both of these are x. They are perfectly correlated. In this situation, what is it that we can say? Expectation fx gx, if you remember, it is, so it is nothing but uniform random, right? So it is in this new norm that I introduced. It is the
It's 1 o'clock.
Okay, so I will just complete this, maybe take 2 minutes and then finish. This is the L1 norm, which we know by Holder's inequality that you can bound it by P norm on one side and P dash norm on the other side, where P and P dash are conjugate exponents. Okay, so that is what we have. What happens when time is infinity? Here we have expectation gx into fy, where x and y are independent. See, the xi, yi are completely uncorrelated. Rho will be 0. When t is infinity, this rho will be 0. Therefore, this expectation factors. If you want to write in terms of without this expectation business, another way to write it is, so if you prefer to write it without expectations, you can write it as f tensor g L1 norm. Okay, so that is one way to write it. You have two different variables for f and g. That's what it means. But let's take this. So which is, of course, what can we say about this? This is bounded by, so what do I want to say here? Yeah, L1 norms, right? On both, we have L1 norms. So we get which is actually equal to, maybe, so we'll write this as f L1 norm into g L1 norm. So this is, so when the same variable is, when you have two independent variables, you get the product of L1 norms. When you have the same variable, you have this Holder's inequality. Okay, so what hypercontractivity is doing is something intermediate. It is saying that expectation f of x t into g of x is less than equal to LP norm of f times LQ norm of G. Okay, how is this coming? Actually, this is just from here. This is just from here. You can okay. So why is hypercontractivity saying this? It is saying that this is QTF inner product G, right? Meaning the L1 norm. It is by which we mean QTF times G L1 norm. So there is a 1/2 to the n here. Sorry. So I should put a 1/2 to the n here. So that is this, and it is bounded by Holder's inequality QTF P. Sorry, let's say Q dash and G Q. Sorry, maybe I make this Q and this is Q dash. Then, but this is bounded by this is Holder's, and this is bounded by LP norm of F times LQ norm of G. Okay, so for T, but for some T, only rho less than equal to P minus 1 over Q minus 1 condition is there. But this is a stronger conclusion than this. What you get by Holder, P and P dash, this is better because P is going to be a smaller number than Q dash, you can check. Okay, P is smaller number than Q dash, so this is a stronger conclusion than something like this. So that's the...
No, I don't get it. So Manju, this where did the Q prime go? The norm of Q prime.
No, this is Q, that is, oh sorry, this is Q prime, sorry. Okay, so this is P and Q prime is what you get, whereas, okay, sorry, this is P and P prime is what Holder's gives. Okay, but P is less than Q implies P dash is greater than Q dash, right? So to getting P and P dash is worse than getting P and Q dash. This is a smaller norm. So this is a better inequality valid for this when the X variables are correlated. That's an interpretation of this hypercontractivity inequality. Okay, sorry, I have gone 5 minutes over time. I will stop, but I can take any questions. So let me stop the lecture here. I can repeat some of this also next time. If this Holder inequality thing, people please go over it. If it's not clear, I will repeat.